not Archimedean, because it's Conrad's idea to do this. So it's Conradian if C is normal in D, and quotient ordering on D mod C is Archimedean. Right. And remember, the ordering on this quotient is just defined by looking at coset representatives, right? So it's not some mysterious thing. And in this case, we can apply Hölder's theorem to this jump and get an embedding of this group into R plus, right? So let's just say that such a homomorphism is there and it has a name as well. So in this case, any how it goes from D mod C to R plus that comes from Hölder's theorem is called the Conrad homomorphism. So coming Hölder's theorem is a Conrad homomorphism. Okay. So let me give an example of, just a baby example of this, where we do a short exact sequence construction and point out that if we have an Archimedean order on the quotient and on the kernel, then it gives an example of this thing that we've just defined. So for example, you could do something like this. So suppose G fits into the short exact sequence. And I don't have to say exactly what G is for this to work. So it's just, so it fits in there like this.
Are you saying G is abelian by?
Yeah, I don't want to say that. So here's what I'll do. I'll do my trick to get out of this. It's not 1, it's not 0, it's infinity. Yeah, so G fits into this short exact sequence. Okay, and now what I want to do is say, put an Archimedean ordering on here. And the way to create those orderings is, for instance, the example I did in the first lecture, where you choose a vector of irrational slope and then you look at dot products. So put an Archimedean order using a vector of irrational slope. So I'll just say a V, the irrational slope, and the dot product, as in the first lecture. So you're basically declaring all things to one side of a line of irrational slope to be positive, and you can check that that's Archimedean. Comes out. And then let's give that a name. So the positive cone P, and I'll name these maps I, Q. Right. Then say Q is the positive cone of the usual ordering on Z. And if we just look at, I of P, Q inverse of Q, this defines an ordering and its convex jumps. So it is an ordering G jumps. So entity Z squared, I should say I of Z squared, and I of Z squared. Right, and you can check that there are no other convex subgroups because if you quotient by a convex subgroup, then any convex subgroups that properly contain the one you quotiented by become convex in the quotient with respect to the quotient ordering. And so that's not going to happen here because the quotient ordering is the standard ordering of Z, which is Archimedean. So it doesn't have any convex subgroups in it. And you can even write down the Conrad homomorphisms. For Z, there's not much to say, right? The homomorphism is just send Z into the reals. And the Conrad homomorphism corresponding to the irrational ordering that you put on Z, it ends up being basically projection onto the vector B. So you can write down all the details. Okay, so this is all meant to be evidence that we sort of have defined some sensible kind of order. We can make examples of it. But of course, it's much more general in the language that I gave here. So let me just say the definition that we'll run with then is that a left ordering less than of G is Conradian if for all non-identity elements of G, there exists a Conradian jump C, D, G in D, but not C. And we'll call them Conradian left ordered groups. If this defines a new class of groups, okay, because a priori we don't know that we've actually succeeded, right? So we'll call these groups CLO, Conradian left ordered groups. Okay, so now we need to sort of check where we've arrived, which is that our goal is to make something in between left orderable and bi-orderable. And okay, we've at least succeeded in doing this. Right, and the reason I say we've at least succeeded in doing that is because a Conradian left order is just a left order with more properties. So okay, but the relationship of this with bi-orderability is not clear at all. And it's not clear at all whether or not this is equality, right? So first thing I'll do is say, this is not equality, and let me show why. And then the next thing I'll do is say, and it's related to bi-orderability in the way that we hope, which is that bi-orderable groups are an example of this, but we have to actually do theorem to get there.
Does it follow that G is solvable?
No, thank goodness.
Okay.
It looks like it would be because if you imagine doing this construction just iteratively, right? But the thing is, you can have groups that have Conradian orders with sort of many jumps, not just like a finite.
Oh, it just doesn't have the term.
Yeah, exactly. So you have exactly the right idea. Like you want something that's kind of like solvable, but not really, because you could have many jumps. And in fact, it doesn't even have to be sort of like if you look at the ordered set corresponding to the convex subgroups, it doesn't even have to be nice. It could have like, you know, some limits and things like this. And, yeah.
Does every torsion-free countable solvable group have a Conradian order?
Yes, I think so. Well, it has to be left orderable.
Sure.
Yeah.
Sorry,
Okay.
just a simple question. Suppose you have an abelian group, like let's say just Z squared.
Yeah.
Does it have orders, left orders that are not Archimedean?
Yes. Yes.
Okay.
A lexicographic order on an abelian group and a torsion-free abelian group will never be Archimedean because the elements inside of any convex subgroup, like if it's lexicographic, that means that the kernel is going to become a convex subgroup. And the elements that are inside that convex subgroup are sort of, their powers are bounded. Does that make sense?
Yeah.
Yeah, so it's never going to be,
Thank you.
lexicographic orders are never going to work. Okay, so how do we show that this containment is proper? We need a theorem. If G admits, so I'll say the theorem first and then I'll define the term that I use in it. Conradian LO, then G is locally indicable. I'll just say definition. G is locally indicable if for all finitely generated subgroups H in G, there exists a surjection from H to Z. And because of how I've defined Conradian orderability, that's hopefully not going to be too much of a surprise because you already have all these maps into R plus, right? So all we need to do is organize our thoughts carefully in order to see why this works out. So I'll just say, let's take a finitely generated subgroup of a Conradian left order group. So let's suppose G admits a Conradian left ordering.
You want that surjection to be a homomorphism?
Okay, yeah, a surjective homomorphism. Yeah, thanks. So so start with a Conradian left ordering of G. Take H and G finitely generated. Say it's generated by H1 up to HK. And suppose that we've ordered the generators so that they're all positive and they get bigger as we go up in index. We can do that because if there's some generator that's negative in our first choice of generators, just flip them and choose take the inverse. And then just adjust your indices so that this is true. Okay, then take the jump corresponding to that biggest one. So then consider CD corresponding to HK. So that means that HK is in D, right? And the identity is certainly in D. So by convexity, all the generators are in D. So actually H is in D. So by convexity, H. Now all I want to do is I just want to say, well, now use the Conrad homomorphism corresponding to that jump. But I have to be, just a tiny bit more careful than that. So first note that C does not contain H, right? Because this one is outside of C. And so if I use the Conrad homomorphism, this thing at least is going to have a non-trivial image under the Conrad homomorphism. So I'll say, now if we look at tau from here to here, and I'll just say applied to H mod H cap C. I mean, I'm being a little sloppy here, but that's what you want to do, right? Then what you're going to do is you're going to get a non-trivial image of this finitely generated subgroup inside of this torsion-free abelian group. So certainly you can maybe compose this with another map if necessary to get a map onto Z. So we get a homomorphism from H onto a finitely generated torsion-free abelian group. And that's enough. So because of this result, if I want to show that the containment Conradian left order groups inside of left order groups is proper, I just need to show you that there's a left order group that's not locally indicable. Easier said than done. I can't actually do that without invoking some stuff that I don't have time to cover. So I'll just say the place where you find plenty of these quite easily is three-manifold theory, or even low-dimensional topology. There's stuff coming from the Bray groups, but I can't really write one down and do all the nuts and bolts on the spot. So I'll give you a presentation of such a group, and you can confirm for yourself the group is perfect. But then I'll just say, and it's left orderable because of some high-powered stuff, and I think we'll have to leave it there. But it works. So, example, this is a LO, but not CLO group. And the reason it's not writing left orderable is it's going to be perfect and finally generated. So here's what I want to do. Just take G to be this, X, Y, Z. X squared equals Y cubed equals Z to the 7 equals X, Y, Z. And a lot of people probably recognize that group, but I'll just say it's a group. And you can verify just from the relations that this group is perfect. So, has trivial villainization. And you can also verify that this group acts on R effectively, so that you can give it a left ordering. And if you know where this group comes from, the way that you do it is, so we can hook up an action on R. And the way that you do it is you take a representation into SL2R and you lift it to SL2R tilde so that you get an injective homomorphism here. SL2R. So there exists injective. And we sorted out yesterday at great length that this acts on the circle. Great. And then you can look at the universal cover, and that's going to act on R. And the action on R makes this left orderable, and the embedding makes this left orderable. But I'll leave it at that. So this applies G is LO since SL on R. So it's on R. Okay. Yeah.
Why does perfectness implies that it is not locally indicable?
Oh, because if the group were locally indicable and finally generated, then the group itself should have a surjection onto Z. Yeah, but doesn't, so. Yeah.
Does the converse of the theorem hold by Burns-Hale? Is there more going?
Yeah, that's where we're going. Yeah, yeah. So what I want to say now is, okay, well, we have to do something else first. We have to sort of investigate the relationship between the new kind of ordering that I have by orderability. And then once we have that out of the way, then I'm going to say, okay, now we seem to have something new in our hands. Can we just run the machinery from the first lecture where you do this stuff about choosing exponents and then use it to do Burns-Hale? And, yeah. And then we surprise ourselves at the end. Okay. So, yeah, does this make sense then? So, so now the place that we've arrived at that is a little bit challenging is this. So I'll say, what about orderable versus Conradian left orderable? Because from the definition that we have, it's not really obvious that these should be related at all, because biorderable is something about elements, right? Where you take elements in the group, G and H, for instance, and if H is bigger than the identity, then so is G inverse bigger than the identity. Like that's all we have to go on, really. So what I have to do is I have to relate the definition that I gave to a property like this. And it turns out that is possible, but definitely beyond the scope of a 1 hour lecture. Let me say it here. Let's just do to Conrad. So for a left order of G, following our equivalent. So 1, this is Conradian. 2. So for all G, H, in G positive, there exists positive n such that G is less than HG to the n. Or 3, actually you can use n equal 2. So same as 2, but n equals 2, i.e. G and H are positive, and G is less than HG squared. And I'll say I don't actually think this was in Conrad's original paper, and I don't know where the first place this was written down was, but the first person that I learned it from was Andres Navas. So thanks to him for pointing that out. So the way to prove this is pretty, so the difficult part, I'll say, is starting with 2 or 3 and getting to 1. That's quite bad. And I don't know any way that's slick and clever. Really all it is you get in there and you just sort of struggle your way through it using lots and lots of fancy, clever inequalities, and then somehow at the end it all works out. This way to this way, though, that does sort of have a sensible way of looking at things. And you can see why 2 suffices from just going through, a few steps of the proof. 1 implies 2. And so let me do that. And how much time do I have? Yeah, let me do that. And then you'll see why 2 suffices. And it will sort of give some plausibility to this, at least.
The question in the chat.
Oh, it just says, will you be recording the lecture by Ty? So yes, right? There, okay. Okay. So I'll say proof, sort of, and we're just going to do like 1 implies 2. And this is just to give this some sort of hint of plausibility, because right now it probably just seems like magic, right? So how would you do it? Well, take 2 positive elements. And what we have to work from are all these Conradian jumps and homomorphisms onto R plus. And they're all order preserving, because that's what Hölder's theorem gave us for each Archimedean ordering on the quotient. We get an order preserving map into R plus. So to show G is less than H, we'll actually just do squared, right? Or the n. To show this, we'll check that the identity is less than G inverse H G squared. So how do you do that? Take the jumps for each. So consider CG, DG, and CH, DH corresponding to G and H. Now you just do possibilities, like you do cases, because the convex subgroups relative to any ordering are ordered by inclusion. So either these jumps are the same, or this jump is sort of smaller than this jump, meaning DG is contained in CH, or this jump is bigger. I'm sorry, this jump is bigger than this one, right? Meaning that DH is contained in CG, and you just consider cases. So let's do one of those cases to see what happens. So okay, there's 3 cases. Let's do one. For example, let's say that this jump is the bigger jump, meaning that DH is contained in CG, i.e. G is the bigger jump. I don't know how else to say it colloquially. So then what we want to do is just look at the Conrad homomorphism corresponding to G. Consider tau from EG, CG are plus. This is order preserving. Now I want to plug in this G inverse H G squared. Right. And the point is, because we're assuming that DH is contained in CG, H is killed, right? So that's gone. And what we're left with is tau of G inverse plus tau of G squared. And when you know it, this is an abelian group, so it all works out because G is positive, which means that the image under this tau has to be positive. So right, this tau is order preserving. So there you go. And then you do the same for the other cases. And you see, this is why 2 works, because I only needed a 2 here to cancel out that -1. But you see, if I had a big N, that would also do it. Okay, so I'll say check the other cases, and that gives you one direction to the theorem. The other direction, starting from here, and going backwards, is, like I said, very nearly intractably hard, difficult, at least almost intractable for me, at least.
So why was the original version stated with the
So my understanding when in reading Conrad's paper is that the original version is stated with the N because going this direction in the proof, it only really feels possible with the N and not with the 2. You would have to first show that like somehow you're choosing really big N's. I don't know, like when you read the proof, having this definition makes it easier to do things combinatorially. Yeah.
It feels like it should be easier when you have a concrete 2 to go.
Yeah, I agree. But in the original paper from like the 50s, if you read it, there's N's everywhere, and the N's really do make all the proofs in that paper go more smoothly. But then sort of later work, 2 definitely helps. Yeah.
Adam.
Yeah.
So in the proof, if you take n equal 1, you don't get a positive number, right? So in your second case,
And should
You-
be greater
n
than
should
1.
be greater than 1.
Sorry, what?
You have to put n at least 2.
Oh, and yeah. So I need to say N at least.
At least 2.
That's not correct. No. It's
No, but that means that you have to find another argument for n.
yeah. That's exactly yeah, exactly. No, this is correct.
Yeah.
But the heuristic thing I'm doing over here is yeah. Yeah, you're calling out a gap in my heuristic proof is what it is. Yeah. You had me for a second though. Okay. So how much time do we have? Yeah, okay. So now what I want to say is that from this, and this is why I didn't want to change that. I want to be able to say for bi-orders, we know the relationship now because of that result. So I'll say a corollary is that every bi-order is Conradian. And it's just because if G and H are bigger than the identity, then G inverse GH It's bigger than the identity. And so there, that's n equals 1 is working, right? Yeah. And so therefore what we have is bi-orderable groups contained in Conradian left orderable groups contained in left orderable groups. And we know that this is proper. And so far we know that at least there's a containment here, but in one line I can tell you, and that's proper. So the group x, y, x inverse equals y inverse shows that this is proper. This is definitely locally indicable. Just look at the short exact sequence that it's in the middle of. And it's definitely not bi-orderable. So this shows the left containment. So we have something new. Okay, but a legitimate concern at this point would be that, okay, it's new, but it seems pretty funny, right? It's a little bit strange. And so this is where I get to the point and I say, okay, but let's continue our investigation and run all the machinery from the first lecture, where we look at these exponents that you can choose in order to ensure that certain semigroups don't contain the identity, and see what we can get. Yeah.
But why is this? Why does this have a Conradian left order?
Because
Pretty solvable, I guess.
yeah, it fits into here.
Yeah.
You know, it said, yeah. Look, I'm using ones again. Yeah. You've thrown me off. Yeah, so it fits into this short exact sequence, and so it admits a Conradian order just lexicographically. And you can also use the same thing to say why it's locally indicable if that's how you want to look at it.
Did you give general conditions under which a short exact sequence gives you something?
What did you say?
Did you give conditions under which a short exact sequence gives something CLO?
The conditions would okay, I didn't, but the condition is if you have a Conradian left order on the kernel in the image, then you can put a Conradian order on the middle just by doing the lexicographic construction. It works. Yeah, but I didn't say that. You're right. Okay, so here's what we can do. Run the machinery from the first lecture. And so here's what you would get if you did that. And so I'm just going to say something that looks exactly like the theorem from the first lecture about choosing exponents with one small change. I have to sort of imagine that I'm extending a semigroup to give a Conradian order. So that means I got to do something like this. So this is a semigroup satisfying if G, H are in Q, not the identity, the inverse in G squared is in Q. So start with that. Don't just start with the semigroup. Start with that. So then there exists positive cone P of a Conradian ordering of G with Q minus the identity contained in P, if and only if Q satisfies star, where a star is something that I have to write down now. Star is for all finite subsets, non-identity elements. You can choose exponents such that the identity is not in. Now I'm going to write something mysterious and then we have to say what it is. CSG. You can probably guess what it is actually. E1 to epsilon 1. Here, this is the smallest semigroup that contains all of these guys, plus closed under this property, taking two elements that aren't the identity and adding that. So or CSG is the semigroup containing the indicated set. U minus the identity, all of these guys, Gi the epsilon I. And if G and H are in there, not the identity, then this product is in there. So that's the statement you would prove. And this is the property star that you would need, and you run the exact same proof and it works. I will say there is one major bit of extra work you need to do. When you get to the point where you define this totally ordered, this partially ordered set, and you want to apply Zorn's lemma, you need to check that chains have maximal elements. That ends up being a lot harder. It's still just take the union, but it's harder because of the fact that it's not a semi-group now. You have this funny thing. Okay, so then you get all sorts of good corollaries, which is that G is Conradian LO. If and only if, we can say the same thing. For every finite subset, you can choose exponents such that the identity is not contained in CSG of that finite subset. So for all finite subsets, G1, Gn, in G, but not the identity, there exists epsilon I plus or minus 1, such that the identity is not contained in this. And it's just the same as before. You apply this theorem, but you take Q to be the identity. So now we can do the same thing as before and say that if all finitely generated subgroups are Conradian left orderable, then the group is Conradian left orderable, for instance. And we're also in a position to try and do Burns-Hale all over again. So let's do it in 3 minutes. So not really, we're just gonna write down what happens when you try and run Burns-Hale.
Can this like a G square be replaced by other powers like G cube or?
Yeah, so here's what happens. You really need to use just G squared here. If you allow yourself maybe there exists an N definition, then you run into some issues proving that Zorn's lemma is going to apply. Or the other techniques that I know of doing this involve setting up a compactness argument in some space. If you allow just arbitrary n bigger than 0, you run into compactness problems and the argument doesn't work. Once you boil it down to just 2, then somehow it's okay.
Just some uniform bound word, or still you need.
Yeah, probably an arbitrary uniform bound would work, I think, because you just need like finite. Okay. So let me say the last few minutes theorem, and I like to think of this as the Conradian every locally indicable group. It's Conradian left orderable. That might just come out of nowhere, but let me say why. If we really just ran the Burns-Hale proof, we would come up with a proof with a theorem that says something like, if every finitely generated subgroup surjects onto a Conradian left orderable group, then the group is Conradian left orderable. But we just saw earlier that finitely generated Conradian groups, like they surject onto Z, they're locally indicable, right? So in the statement of that theorem, the assumption finitely generated subgroups surject onto Conradian left orderable group. That's the same as assuming on the Z. And so you can just write it this way. But this means we combine this Conradian Burns-Hale with the earlier observation. We have CLO if and only if locally indicable. And I would say that that means that this sort of bizarre definition of a new kind of ordering that we made is, justifiably a good thing to do, as it boils down to a sensible group theoretic property. So in the end, what we have is we have viable groups properly contained inside of CLO groups, which are the same as locally indicable. And these are all LO. In the closing seconds, I'll say, fair question at this point would be, okay, you found one thing in between here and here. Are there other things that we missed? And the answer is, there's one other thing that I know of. There's something that can go in here properly, which is called recurrent orderable. And this is due to Dave Morris. But for reasons that I won't go into, that ends up being something that's quite difficult to work with and hasn't sort of been investigated in a lot of depth. But it is strictly between these two. I won't even bother defining it. So anyway, that's it for lecture 3. Thanks. Any questions?
What would you position outside of left orderable, larger than it, that would still have a similar flavor?
Oh, yeah, that's what I'm gonna do next lecture. I'll tell you what I'm gonna do. I'm gonna motivate it. I won't give it away. But what I'm gonna do is I'm gonna say, one of the nice properties that left orderable groups has is that they satisfy Kaplansky's zero divisor conjecture. And so I'm gonna do a little proof of that and then say, based upon this proof, what properties would we want to keep? And there's sort of two obvious guesses. And then I'm gonna come up with two things between LO and torsion free that all the length. Yeah.
What was the history? Like, was the CLO definition given and they were like known to be locally indicable or expected that it's equivalent, or was it sort of a?
In the first paper where this came out that I'm aware of is there's a paper by Conrad in 1959. And in that paper, he gives there exists an N definition, but then goes through and shows that there's many other ways of writing down that inequality, like there exists an N kind of things. It shows they're all equivalent. And also, I think, did he do local indicability in that paper as well? Do you know? I think not.
No.
Yeah, it was just many different kinds of the same inequality. Yeah. But then it came later that the observation that this inequality implied that all these quotients were Archimedean, and then you could just create all these maps, this whole Hölder's theorem. And I defined it that way instead of the N thing. Much easier to work with.
Going back to Riley's earlier question, I think Riley was the one who asked it about whether Conradi and left orderable group have to be solvable. It seems that now we have classic counterexamples, because for instance, hyperbolic three-manifold groups with positive Betty number would have to be Conradian left orderable by this theorem. But
Yeah.
what do their Conradian orders look like? Is that a reasonable thing to ask?
Yeah, that is a reasonable thing to ask. So what do they look like? I mean, so of course you have to sort of frame that question in some way to make it make sense. The way that I would interpret that, like what do their Conradian orders look like, is I would think of the space of all orders and how do the Conradian orders sit inside there. And this is something that Andres will talk about, but I'm sure I don't want to. Yeah, and so that forms a compact subspace of the space of all left orders, and sort of how that space is sitting inside of the space of left orders is something that people have worked on a lot. I mean, a big restriction comes from the fact that if you're working with a finitely generated group and it has a Conradian order on it, then you know that the Conradian order has to arise lexicographically from some map onto a torsion-free abelian group, just because the group being finitely generated means that it itself is going to have a Conrad homomorphism to R plus. So at the sort of, in the big picture, they're sort of not that interesting because they all arise lexicographically, but.
So one way to invent a class in between local indicable was to choose another target. Instead of say cyclic groups, you could choose some particular class of groups with an ordering, and then say locally in that target, and then you'll have invented something in between.
Yeah.
Are there any favorites?
Not that I know of, but I could tell you another trick that might give something new. I think it's the subject of an open question and by this guy here. So if you interpret Conradian left orderability as saying take any two positive elements, then this particular word always is positive. Why don't we just replace it with a different word, right? Why this one? And so if you just try different words, see if you get something new. Do you? I don't know if anyone knows the answer to that. That's the attempt that I know about. And yours, I'm not sure. Right? But I see what you mean, like just project onto different, something other than Z. I don't know. Yeah.
What sorts of order types of jumps can show up? Like for a Conradian left orderable group?
Oh, you mean like if you look at the ordered set of convex subgroups, like what's the order type of that?
Yeah.
Oh, I'm pretty sure you could engineer a group to give you just about anything, because you would probably try to do something using like abelian groups or something like this, and then just build like a ridiculously huge abelian group doing exactly the bad thing you wanted or something. Yeah, because all you need is torsion free. And then the abelian group is going to be orderable. It's got a lot of flexibility to just
What about for free groups?
free groups. So you're asking like, what kind of jumps do you get there? Oh, you can get all sorts of crazy things. So you can get the easiest kind of orders to think about that are Conradian are obviously bi-orders. And what you can do there is create an easy class to think about would be if you just use like the quotients of the lower central series and you order all of those, because those are all going to be torsion-free abelian groups. And you can sort of pull back the orders from the quotients of the lower central series onto the free group to create an example of this kind of order. And it's actually a bi-order that's central. So that's one way to make easy orders. But on the other hand, you can put left orders on the free group that have no convex subgroups at all. So if you start asking what are the jumps, well, there's one that goes from the identity of the whole group and there's nothing in between. So yeah, the free groups are, there's just sort of too much freedom to do crazy things. I mean, a good example is like on torsion-free, on the nilpotent groups, if they're left orderable, all the orders of this are of this kind. So that's sort of the good case to look at.